Chapter number 12, we want to talk about oxidation states. We're going to learn about reduction oxidation reactions or redox reactions, which are the basis for how batteries work. Okay? So what's going on in that little battery that you have, that's a chemical reaction that's taking place inside that battery. And this is the basic concept behind that. So let's talk first about oxidation states. And electricity involves the flow of what? Does anybody know? The flow of electrons. So electricity is the flow of electrons, okay? And so if we're going to consider chemical reactions and how they're related to electricity, then we got to keep track of electrons, all right? So let's look at a reaction like this. This is a decomposition reaction. Do you guys remember what a decomposition reaction is?
When you break up and into its individual elements.
Right. It breaks up into its individual elements. So you start with a compound and you want to break it down to its individual elements. And so what you do, if I were to just say you have the decomposition of NaCl, and you were going to ask you to do that for me, you would write down NaCl on the other side. And the other thing that you'd have to take into account here is if any of these guys are homonuclear diatomics, right? Since they're appearing by themselves, we know Cl is, so when it appears all by itself, it's going to appear in pairs. And then you just balance that equation. So you put a 2 here and you put a 2 here, and you balance. So that's the decomposition reaction for sodium chloride. Sodium chloride is an ionic or a covalent compound? It's ionic, right? How does she know that? Because it has a metal, right? We're just looking to see if it's got a metal in it with the non-metal. So if it's got a metal, then it's ionic. And if you remember, there was a diagram, there was a picture somewhere in the book that kind of showed like what was supposed to be a microscopic view of an ionic compound. If you remember with the ionic compounds, you have like this lattice of all the ions kind of side by side one another, the plus and the minus ions. And so you've got this lattice of all these positive and negative ions beside one another. And so if those guys break apart into this, remember what you've got over here is you've got Na plus and you've got Cl minus, right, as ions. Well, I didn't write any charges on any of these guys over here, right? And if we write them, if they've got a net charge, when we write them by themselves, we've got to add that charge into the chemical equation. I didn't do that. So how is it that the Na, if it's carrying a positive charge here, and the Cl is carrying a negative charge, why is it that they don't have any charge over here? Why does the Na not still have a positive charge? If it's got a positive charge, what does that mean? It's missing an electron. It's lost an electron, right? So where's it going to get that electron from so that it's not positively charged over here? Well, it got it from the Cl, because the Cl has an extra electron, right? It's negatively charged. So that's what happens as it moves over here. So the point is, there was an exchange of electrons, right? And that's what happens in these redox reactions. So over here on this side, we had a 1 plus charge on this Na as an ion, and we had a 1 negative charge on this Cl as an ion. But both of these guys are electrically neutral. And so you see then as we move from left to right in our reaction, this guy gained an electron, because it became more negative. Since it was positive before, it gained an electron and became 0. This one lost an electron because it became more positive. It went from -1 to 0, right? And these are what we refer to as the oxidation states, these numbers down here. That's the oxidation states for the individual elements in the reaction. And these oxidation states will change from one side of the chemical equation to the other side if it's what we call a redox reaction, a reduction oxidation reaction. Okay? Now does that kind of make sense to everybody? That should sort of make sense to us as we talk about ionic compounds, because we know those ions already carry charges, and so it would sort of make sense that, when we talk about electrons moving and that sort of stuff with ionic compounds, that kind of makes sense to us. But it also applies to covalent compounds. It's also relevant to covalent compounds. So oxidation state going to say this is when analyzing covalent compounds. You have to think about the covalent compounds like this. Oxidation state when analyzing covalent compounds is the charge on an ion. Well, that's for the ionic compound. On an ion or in a molecule the charge that an atom, and when we say an atom here, we're talking about a single atom, would have if the shared electrons in a bond were always given to the more electronegative atom. Okay, I'll let you write that down and then we'll talk about it. So you guys remember when we learned about electronegativity? Can anybody recall electronegativity had to do with covalent compounds and what we defined electronegativity as? Like if I've got two elements in a particular covalent compound and one is more electronegative than the other, what does that mean? Yes?
How strongly the electrons are attracted to.
That's right. How strongly its pull is on those shared electrons, right? So the more electronegative an element is, the stronger it pulls on those electrons. Does anybody remember what we said was the most electronegative element in the periodic table? It's in the top right, but not a noble gas. Yeah, fluorine. So electronegativity was one of those things that it was like as you went to the right and up, it was the periodic chart got more electronegative in that direction, right? And so when you think about covalent compounds, when it comes to oxidation states, don't think about them sharing the electrons, but think of the more electronegative atom actually taking the electron. And that's how we think about oxidation states in covalent compounds. So when you have a compound like HCl, which is a covalent compound, if you remember, H has one valence electron, and Cl, which is in column 7, has 7 valence electrons. And so these guys will share these electrons, so both of them will be ideal. If you remember back when we did Lewis structures and we talked about that. And so it looks like this, right, with a single pair of shared electrons there. But Cl is in column 7a, just below fluorine, and so it's more electronegative than H is. So when we think about it for the sake of oxidation states, you need to think about it like this. H loses the electron because Cl wins the battle, right? And Cl gains an electron, so now that it's got an extra electron, it has a -1 charge. So that's how we need to think about covalent compounds when we're determining oxidation states. Okay? Let's do a couple examples and see if that'll become a little clearer. Our example is on page 359. And it says, what are the oxidation states for the atoms in Al2O3? All right, Al2O3. Is that an ionic or covalent compound? Al is aluminum. You think that's a metal or a non-metal?
No.
It's a metal, right? So if we got a metal in it, what have we got? Ionic or covalent? Ionic, right? And so if it's ionic, all you got to think about is what are the charges on the ions, and then you will know the charge of the you'll know the oxidation state. Okay. So Al is in column 3A. Is that correct?
Yeah.
It is. How did I know that? O is in column 6A. I knew that too. How? Because I have the whole periodic table memorized, of course. Not? No, I knew that because I did the reverse of swap and drop. You guys remember that? I figured out the charge because we already had a balanced compound. It was already, the numbers were already correct there. So I just swapped, and instead of dropping, I swapped and lifted, right? And figured out what the oxidation state was. So for Al2 and O3, if I gave you that compound, I would just on a test or a quiz, I would just expect you to write a 3+ below Al and a 2- below O. Okay? What about the oxidation states for CF4? All right, so CF4 is not an ionic compound; it's a covalent compound. So this is one where we're going to have to think about. We're going to have to think about it, even though it's a covalent compound. We're going to have to think about it like an ionic, in that instead of sharing the electrons, it takes the electrons. Which is it, the carbon or the fluorine that's going to be more electronegative?
Fluorine.
The fluorine. We said that's the most electronegative element, right? And so if we remember the Lewis structure for this guy, C looks like that, and F looks like this, right? And we've got 4 of those guys with 7 valence electrons around them. Right? And so what happens is they orient themselves around the carbon, and the carbon ends up sharing its valence electrons with all of these guys, right? Sharing with each of those. But since the F is more electronegative, we don't want to think about it as sharing it. We want to think about it giving all of those up. So C then, since it got rid of all 4 of its valence electrons, what's it going to have a charge of? Plus 4, right? Or 4+ is usually how we write that. So C4+, and then F, each of the F's are going to have an extra electron, so each of the F's are going to have a charge of what? Just 1 negative, right? Because there's only we're just talking about one. For each individual F, it has a -1 charge. So then what I would expect you to write down as far as the oxidation state goes is a 4+ below the C and a 1- below the F. Okay? Is that clear to everybody? All right. I'm gonna give you some rules now that that's how to think about it from when you look at the electron dot structures, right, or the Lewis structures. But I'm going to give you some 7 kind of simple rules that you want to really have to think about the Lewis structure. I just wanted to show you how it works, why those charges make sense. What are our 7 rules for determining the oxidation state? Rules for determining oxidation states. All right. The first 5 rules you can think of as always being true. Okay, always true. 1 through 5. So for ions with 1 atom, oxidation state is charge of ion. So in other words, if you have Cl minus, just has 1 atom in it, then the oxidation state of Cl will be 1-. Okay? all elements and homonuclear molecules we've learned 7 homonuclear diatomics. That's molecules that always appear in pairs. That's what the di in diatomic means, 2. But some molecules appear in more than just pairs. You may have 8 of that molecule. As long as it's the same, you may have 8 of that element. As long as it's a single element, then it's called a homonuclear molecule. All right. So this is a molecule that's made up of one element. The oxidation state of each atom is 0. So if we have Fe, or if we have H2, or if we have O3, all of these are going to have an oxidation state of 0. Three. For molecules and polyatomic ions, the sum of the oxidation states must equal the total charge. So NaCl, you've got a molecule with 2 ions in there, but because there's no charge listed on the total thing, the total charge is 0. If you have something like the polyatomic ion OH negative, since the charge is listed, the total is 1 negative. So O and H, the individual oxidation states of O and H have to equal a total of 1 negative when you add them together. All right, number 4, the oxidation state of F in any compound is 1 negative. Remember, F is most electronegative. And then the last of our always true rules is that in covalent compounds, and polyatomic ions, H is 1 plus. All right, so for these first 5, these are always true. All right, now I want to give you 2 more that are usually true. And for these, only use if first 5 don't apply. Okay? So these are usually true. 6 and 7 are, in most compounds, oxygen is 2 negative, that's its oxidation state. And then group 7A elements, fluorine, chlorine, and the ones that are below that, especially chlorine, are usually, what do you think? What charge do you think the 7A elements are going to have? What oxidation state? 1 negative, yeah. It's like the same thing that shows up in the ionic compounds, right? Because remember, our covalent compounds, they're just, when we talk about oxidation state, let me write that a little clearer. We're kind of thinking about them like ionic compounds because they're not, we think about them not sharing but actually taking the electrons. So they're sort of behaving like they do in ions. So that makes sense. In fact, a lot of these, if you sort of think about it like that, they kind of make sense. It makes sense that oxygen would be 2 negative because it's in column 6A. So oxygen is usually 2 negative. You just have to remember, only jump to these steps here if the first 5 don't apply. But you can, in these problems, you can always count on the first 5 being true. All right, so the easiest way to kind of get a handle on these is to start actually doing some problems. So there's several examples on page 361. I think about 6 different compounds that they ask us what the oxidation state is. So I want to go through these 6 and see if we can figure out which of these rules apply as we're determining oxidation states, okay? Just want to make sure everybody got everything copied down?
No.
No?
My hands are hurting now.
I know, really. I hate to write anything out this long, but you got to know all these rules. So it's longer to write down than it is to memorize it. Like once you start using it, they'll come pretty quickly. You'll remember them. All right. Well, here's one. Let's do the first example. S8. S8. Which of our rules there will help us with S8?
Number 2.
Number 2, right? It's a homonuclear molecule. It's a molecule made up of a single element, right? And so the oxidation state for any homonuclear molecule is always 0. Now, I said homonuclear molecule, but when we're writing down these oxidation states, we're writing down the oxidation state for a single atom. So the oxidation state for a single S sulfur atom in this molecule is 0. Okay? What about Al2S3? Al2S3. Ionic or covalent? Ionic. Remember how I told you guys the quick way to do the ionic ones? Do the reverse of swap and drop, right? Swap and lift, or swap and bump up. I'm here to pump you up. You guys probably don't even know what that is, right? There were these 2 guys, this old like Saturday Night Live skit years ago. All right, so we swap and lift, and that'll give us the oxidation state. So if we do that, the 3 moves over here, 3 plus, and the 2 moves over here, 2 negative. So it's basically the state of the ions, right? And so it's rule number 1 is the one that applies to that. We're talking about ions here, and it'll have whatever the charge of the ions are. Okay? All right, H2S. Covalent or ionic? Does it contain a metal? So it's got to be covalent, and it's a covalent compound that has H in it. So rule number 5 tells us that H has to be 1 plus. Let me ask you this question. What is the overall charge of H2S? Do we know what the overall charge is? Unless it's explicitly given, the overall charge is always 0, right? If I don't write the 2 minus out here after this, it's got an overall charge of 0, right? So if the overall charge has to be 0, then for molecules, the sum of the oxidation states must equal the total charge. The total charge of this is 0. But we know that we've got 2 hydrogen atoms, each with a 1+ charge, and so my sulfur atom has to have what oxidation state? Has to have a 2-, because the overall charge has to be 0, right? Because when we do 2 times 1, because there's 2 H's, 2 times 1 minus 2, which is the charge of that guy, it's got to equal 0. Everybody see that? So rule number 5 and rule number 3 apply in this case. So notice again how the 1 was the charge of the individual hydrogen atom. When you write the oxidation state below it, you're writing the charge of just a single hydrogen atom. We don't write the total charge for the H2. We write just the H. All right, let's see CH3F. CH3F. No metals, so we're dealing with a covalent compound. So rule number 5 is going to tell me that H is 1+.
Rule number 4.
Rule number 4 is going to tell me that F is 1-. So since rule number 3 is going to tell me that whatever C is, it's got to be such that when you add all of them together, you get 0. So we've got 3 H's for a total of +3. That's the worst +3 I think I've ever written. An overall +3 charge, right? So +3 minus a 1 equals 2. That was not the way that I should have done that, because that gives you the false impression that this is going to be +2, but this actually has to be a -2, right? Because we want everything to add up to 0. So that whenever we do +3 minus 1 minus 2, we get 0. Yes?
I'm confused about the adding. I'm not understanding it.
Okay, that's all right. So we want all of these, whatever these charges are, they have to all add up to 0, because again, there's an understood net charge here of 0. Since there's no number written out to the top right of it, we know the overall charge on this is 0, right? So whatever charges we write down here, when we multiply that by the total number of the atoms that are listed, those charges have to all add up to 0. So we can double check to make sure we got it right by writing those down. Now when we write down a math problem, we don't put the negative after it, we put the negative in front, right? So we think of this as -2, we think of this as +1, and we think of this as -1, right? So this is a -2, but even though this is +1, that's for a single H, and we don't have a single H. We've got 3 H's, right? So this is actually a +3, because 1 times 3 is 3, right? And so again, we've just got 1 F, so we've got that. So when we add all these up together, -2 plus 3 minus 1, we should get 0 if we did it correctly. Does that make sense now? Okay. All right. So that's our charge, our oxidation states for that. Any other questions? We haven't gotten down to rule 6 and 7 yet, so you know it's coming, right? NaNO3. Let's see if this is the one. NaNO3.
O3. Well.
NA's a metal.
Na is a metal. So we've got an ionic compound, so we know Na is going to have what oxidation state? If we look up in our periodic table, we see Na is column 1, so Na has a 1+ charge. Okay, that's based on rule number 1. NO3 is actually a polyatomic ion. We might have remembered that. We don't have to remember that, actually. As it turns out, it doesn't matter. We just have to make sure that the overall charge for this compound is going to add up to 0, right? But if you want to think about the NO3 like that, you could remember that NO3 carries a negative charge. And that's what we expect to happen, because if this whole thing here were a 1 negative, then we got a total overall charge of 0, right? But when we figure out the individual oxidation states of N and 0, the only thing that's going to help us this time, we're going to have to drop down for the first time into the usually true section. Because NO3, if you looked at that by itself, it's not an ionic compound, or we could apply rule number 1. We're going to have to drop down here and say, okay, in most compounds, oxygen is a 2 minus. So if I make oxygen a 2 minus here, then I've got a total of a 6 minus charge on oxygen and a 1 plus charge on N. So what does on Na? So what does N have to be in order for this to balance out so that we got a total charge of 0? It has to be a positive 5, right? 5 plus. Right? Does everybody see that? Yes.
Why wouldn't rule number 2 apply for the O3?
Because it's not all by itself. That's only true if we had something like this.
Okay.
Right? You can't, like if I put an N in front of that, then it's totally invalidates that. Right? It's got to be all by itself. Good question though. All right, so this is our oxidation states. Does everybody understand why? You see how those all add up to 0? And then our final one, which is S2Cl2. S2Cl2, and this is our first time that we're going to stay. We're going to stay down in the usually true area. Right here's our first one, Lily. When you were asking that question, that doesn't apply to any of the rules up top here, other than we are going to use rule number 3, but we're only going to use rule number 3 after first we drop down and use rule number 7. We're going to have to assume that chlorine is a 1 negative. Right? So we write a 1 negative down here. Since there's 2 of them, that gives us a total charge of 2 negative. And so then my S2 is going to have a total charge of 2 plus, which means that a single S is going to have a charge of 1 plus. So that's what we want our charges to be. Does that make sense? So remember, you're going to have to do the math. If you just look at these numbers all by themselves, they're not always going to add up to 0. You got to do the math, and like in the case of this one here, where you say, well, it's 3 times 1 plus, which is a positive 3, and then a positive 3 added to a negative 2 added to a negative 1 will give me the 0 total that I'm looking for. All right. Now the goal of this is, we're talking about redox reactions, so the goal of this is to apply it to an entire reaction. So that's what we're going to look at next, but you got to understand these steps to get there. So any questions about this before I move on? All right. I'm going to assume you have it then. Let's move on to actual redox reactions. Reduction and oxidation. Reduction and oxidation. I'm going to try to, I ran out of room in the last class to be able to do all this over here, so I wrote that in a more compact way, so hopefully we'll have enough room to leave those rules on the board. Thinking about this equation, 2HCl H2 plus Cl2. If I were to write down the oxidation states for each of these atoms in this equation, HCl, we would use rule number 5 here and say, well, H is 1 plus in covalent compounds, and so that means that chlorine has to be 1 negative. See how I started with the rule that was up here in this area first? It turned out that rule number 7 was accurate for this one, but because there was a case that was in the top 5, I had to start with that. So I started with 1 plus for H. And then for each of these guys, we have a 0 here and a 0 here, both based on rule number 2. Right? Now notice what happens for these as you move from one side of the equation to the other side. H had a 1 plus oxidation state. It gained an electron and became more negative and has zero oxidation state on this side of the equation. Everybody see that? It was one positive, it got an electron and became zero. This one's one negative, so this has an extra electron right here, but when it moves to this side, it loses that electron and becomes zero, right? So it becomes less negative. And so this is what you will always see if it is a reduction-oxidation reaction, if it's a redox reaction. You'll see that the oxidation state will change for something will be what we call reduced, and something will be oxidized. Something will gain an electron, while something else will lose an electron. Okay? And so we have to verify that that happens in order to determine if it's a redox reaction. So in a redox reaction, the oxidation states change when the reaction happens. In this particular problem, Cl was oxidized because it lost an electron. H, we say, was said to be reduced because gained an electron. And so we've got a cheesy little way to remember which is which, all right? The way that we remember that is that Leo, the tiger, says grr. All right? Leo says grr. Leo is Latin, not tiger, Leo the lion. Leo is Latin for lion. All right, so Leo the lion says grr. And so Leo, Leo loses electron oxidized. Grr gains electron reduced. All right? So if you can remember that, and that's the whole point of being really cheesy, right? So that you'll remember that. All right, so I guess I'm going to have to write this out. I'm going to write this out, and then I'm going to immediately erase it. Well, I won't erase it immediately. Let me just write it over here, so we'll have some room. So let me make this note. If a reactant is reduced, all right, and in this definition here, notice I'm saying that not an atom is reduced, but the reactant that the reduced atom is in. If a reactant is reduced, it is called the oxidizing agent because it oxidizes another reactant. And the reverse of that is true. The reactant that is oxidized is the reducing agent because it reduces another reactant. And again, note we're talking about the entire reactant, not a single atom. When we talk about oxidation states, we're talking about single atoms. But so if we say one is oxidized or one is reduced, again we're talking about single atoms. But when we talk about the oxidizing agent, we're talking about a particular reactant, the entire reactant on the left side of the equation, and the reducing agent will be an entire reactant on the left side of the equation. So we're going to do again a couple examples, and we can identify those, and that'll help you make sense of that. But any questions before I do those examples? Leo says, I'm going to write that down so that we don't forget it. Hand cramps today, right? All right, so we're going to do 3 examples. You guys are still writing. Very good. Okay, for all 3 of these examples, the question is the same. I should have known better than to eat powdery Doritos without something to drink. It's a really bad idea. All right, so for all of these, the question is the same. They're going to give us a reaction. They're going to say, first of all, is this a redox reaction? And then they're going to say, if it is a redox reaction, identify which atom was reduced and which one was oxidized, and then identify which reactant was the reducing agent and which one was the oxidizing agent. Okay, so that's what we've got to do for all 3 of these. So the first reaction, for time's sake, I'm not going to write down the phase like they do, because it's not really relevant to our analysis of this equation. So we've got zinc and copper, and they want us to determine if it's a redox reaction first. So in order to do that, we're going to have to write down the oxidation states, right, of each of these atoms. Well, Zn here, per number 2, is going to be 0. Per number 1, because we've got a charge given right here, Cu is going to be 2 plus. Right here, Zn is going to be 2 plus. And right here, Cu is going to be 0. This is like the easiest one ever, right? like, give me more of those, Mr. Walker, on the test, because it's just all spelled out for you. Is this a redox reaction? Do the oxidation states on the individual atoms in here change as you move from the left side of the equation to the right? They do, right? Zn becomes 2 plus. It starts out as 0, becomes 2 plus, and Cu starts out as 2 plus and becomes 0. All right? So now we have identified, yes, it is redox, right? Now, we have to determine which one is oxidized and which one is reduced. So which one loses electrons? That's the one that is oxidized. So what is it? Cu. So we said Cu lost electrons because Cu went from 2 plus and it became more negative, went down to 0. Does everybody agree?
No, it's Zn that lost electrons.
Zn lost electrons, so you're saying Zn lost them because Zn went from 0 to 2 plus, it became more positive.
Oh, because electrons are negatively charged, so when you lose them, the atom becomes...
When you lose electrons, you become more positive, right? So I'm glad that this happened because that's the tricky part about analyzing this, right? If you lose an electron, it's actually going to become more positive. So the one that becomes more positive is the one that actually is the losing one because we're talking about electrons, right? So the Zn is actually, in this case, Zn is oxidized because lost electrons. Right? That's good because that helps us identify how easy it is to get confused with this. You got to see which way you're going. Cu became more negative, and so in order to become more negative, it must have what? Gained electrons, right? It must have gained some negative particles. So Cu is reduced because it says GER. You gain electrons, you're reduced. It's reduced because gained electrons. Now that we've clearly identified those, whichever one on the left side of the equation contains the oxidized atom is going to be our reducing agent. Okay? In this case, the Zn is oxidized, and it's on, as far as the reactant goes, it's all by itself. So you would just say Zn is because it was oxidized, it's the reducing agent. In other words, it calls the other reactant to be reduced. So Zn is the reducing agent. And this is kind of critical in the way that you write this now. Remember, I told you when you talk about reducing and oxidizing agents, you're not talking about individual atoms like you are when you're talking about the oxidation state or whether it's oxidized or reduced. When you're talking about the agent, you're talking about the entire reactant. Okay? So for this one here, you wouldn't just write down Cu as the oxidizing agent. You would write down exactly how it is on the reactant side of the equation. You would write Cu2 plus is the oxidizing agent. So when you write down the agent part of it, you need to write down the reactant exactly how it appears. When you write down the oxidized or reduced part of it, you write down just the individual atom. Is that clear? I think it'll be clearer with the next example, but so maybe you want to hold, if you got a question on that, maybe you want to hold it until we do the next example. Okay, any other questions? I'm erasing. Good? All right. Okay, CO2 plus H2, CO2 plus H2 yields CO plus H2O. All right, so again, we got to figure out the oxidation states to determine whether or not it's a redox reaction. In the first one, CO2, we're immediately going to have to drop down to number 6, the usually true area, right? So O has got to have a 2- charge because none of the other rules apply. And so if the total charge now, according to number 3, has got to be 0, and this is a 2 minus for a total of a negative 4, then C has to be 4 plus. Everybody see that? Yeah? All right, H2 is all by itself, so H is going to have a 0 oxidation state. Is everybody clear on this? I'm seeing some puzzled faces. Did y'all follow how I got this? Rule 6, right? It says 2 negative on the oxygen, so the total oxygen charge was 4 negative since there are 2 oxygens, and so this had to be 4 plus for that to balance out. All right, CO, again, 2 negative on the oxygen, but now the C here has to be 2 plus so that it'll be balanced. For H2O, that's a covalent compound, so rule number 5 says H is going to have a 1 plus charge. And since there are 2 of those guys, then the oxygen has a 2 minus charge in order for it to balance out. So now, we're asking the question, now that we've got our oxidation states written down there, is this a redox reaction? Does anything change as we move from the left side, from the reactant side to the product side? Does anything change oxidation states? C does, right? C went from 4 plus to 2 plus. So did C become, did it gain electrons or lose electrons? It became more negative, right? It gained electrons, right? So C gained electrons. So GR, gains electrons, is reduced. So reduced. C is reduced. O is 2 minus here, 2 minus here, 2 minus here. O is the same on both sides, but H became more positive. So it must have lost electrons, right? Because it went from 0 to 1 plus. So H lost, E's, so oxidized. Lost electrons is oxidized. Now, whichever one the C shows up in on the reactant side, because the C was reduced, then that becomes the oxidizing agent. So the CO2 is oxidizing agent. The H2, because the H was oxidized, the H2, that reactant is the reducing agent. So you see again, when I'm talking about which one was oxidized and which one is reduced, I'm talking about a single atom. When I'm talking about which one's the oxidizing agent and which one's the reducing agent, I'm talking about the entire reactant. Does that make sense? So I mean, you're gonna lose some points, right? If you said C was reduced, so C is the oxidizing agent, you're gonna lose some points for that because you should have told me the entire compound that C was in on the left side. All right, final problem. Any questions? This one's a little bit simpler overall, but not initially. I'm gonna erase these this time. See if we can do some work from memory on the rules. All right, so the last one is FeCl3, FeCl3 plus 3NaOH, 3NaOH, FeOH3 plus 3NaCl. All right. FeCl3, what kind of compound? Ionic. Fe. In the first class, I made the mistake. I read this too quickly, and when I read Fe, I read just F. So I read fluorine, and I was like, oh, this has a 1 negative oxidation state. And then I started, and I looked at the Cl, and I went, oh, how's that going to balance out, right? That's iron. That's Fe, iron. Fe is in column number Well, I don't even
You're
really
not
need to
gonna
know.
guess?
I don't even really need to know because it's an ionic compound, so I can just swap and lift, right? So I can say Fe, I can say that Fe has a 3 plus charge, and the Cl has a 1 minus charge, right? It's just the reverse of what we do when we put together ionic compounds. Cl's in column 7A, so it has a 1 negative charge. Fe's in column 3A. NaOH. NaOH is again an ionic compound. Na is a metal, and so Na is in column. This was a little bit harder because it's not just 2 elements, right? It's Na combined together with a polyatomic ion. But Na is in column 1A, so it's going to have a 1 plus charge. OH is a polyatomic ion, right? But with a total charge of 1 negative. But we can use our rule with hydrogen because these two together do not contain a. Actually, it says polyatomic ions, doesn't it, in our rule number 5? I was trying to think of the best way to explain that. Now that I think about it, rule number 5 says if it's in a polyatomic ion, hydrogen always has what? 1 plus charge. So that means O has to have a 2 negative for this whole thing to be equal to 0. All right, FeOH3 on this side, again, 3 plus. I can swap and lift because this, if I think about these together, just bring the 3 over here. OH is going to have, OH again is going to do the same thing that it did here. We've got a 1 plus charge here, and we've got a 2 minus charge here. And just to verify that the math all works out, if we bring this down, we've got a 3 plus from the Fe. We've got 2 negative times 3, so we've got a 6 negative here. And then we've got a 3 times a 1 plus, so we've got a 3 plus here. So sure enough, the math works out, and we get a total of 0. And then finally, NaCl, that's an easy one. 1 plus, that's in column 1A, and this is in column 7A. So we've written down all of our oxidation states. But look, Fe doesn't change. Cl doesn't change. It's the same on each side. Na is the same on each side. O is the same. H is the same. So is this a redox reaction? No, it's not. Everything's the same. So the hardest part with that was making sure you could figure out those oxidation states. This one definitely was the most complicated one, especially with this guy here, in figuring out the oxidation states. It wasn't particularly hard. It's just that the math's not immediately obvious like it is in some of the other ones.
You just have to make sure they all equal 0.
Make sure they always add up to 0, right? All right, any other questions? No? Any questions about the last test? Take it home. Any questions on how many broken bones we had on our trip? We had the same number of broken bones as the oxidation state for homonuclear molecules.
0.
That's right. Yes. All right. You guys have a good rest of your week. I will see you, Lord willing, in a week.